students. In today's lecture, we will try to understand some more aspects of Debye shielding, and we will try to answer some questions related to the assumptions that we have made in deriving the Debye potential. So, if you remember, the basic assumption that we made while obtaining an expression for the Debye's potential is that we assumed the number density of, let us say, electron to be varying according to the Maxwell distribution, which is E phi by kBt, where phi is the potential, right? And the charge density that results inside the Debye sphere is basically due to the difference of number of electrons and number of ions, right? So, this is the charge density, right? So, number of electrons are larger within the Debye sphere because they are attracted towards the positive charge, and all of them are within this sphere whose radius is lambda d, right. Now, here while we were doing this, we assumed the number of ions to be equal to n infinity, and we assumed that the temperature of the ion was never considered. That means that there is no distribution of ions as such, and that is why we have cancelled this n infinity outright, and we were left with only this E phi by kBt, right, which also means that electrons are being heavier, they are not moving, or this potential is not influencing the ions, they will constitute a constant background, all this, right. Now, we will take a situation in which number of electrons and the ions, both of them are distributed according to their respective temperatures, let us say Ti and Te, and then we will try to find out what is the expression for lambda d and how this expression of lambda d will be a function of the temperature of both the species Te and Ti, and we will look at two different cases in which the number of ions, or if the temperature of ions becomes very large in comparison to the temperature of electrons, and vice versa, right. So, this is going to be an objective of today's discussion, and then subsequently we will derive, or we will actually solve a numerical problem, and which will actually conclude the entire discussion of the Debye's shielding or Debye's potential and everything. Looking back, the Debye's length lambda d signifies the distance over which a particular electric field or charge's presence will be made invisible after that particular distance, and lambda d is, if you compare lambda d to the length scale of the plasma system, it should be very, very small in comparison to this. This is probably the second plasma criteria that we have obtained, and the third one is, using lambda d, we derived a parameter called as Nd. We call this parameter as plasma parameter, plasma parameter. It tells you how many number of electrons, how many number of charged species are present within the Debye sphere, and we have seen that for an idealized ionized gas to be called as plasma, the number of particles must be very, very large, and the first plasma criteria was omega p tau c should be much greater than 1. So, put together these three conditions are known as plasma criteria, and validity of these conditions is a must for calling an ionized gas as a plasma. All right. Now, looking back, if you remember one equation that we have derived, we will write that equation, and that equation is the basis of today's discussion, which is d square x by d r square minus x by lambda d square is equals to 0, where x has r phi and phi is the Debye's potential, right. So, this equation tells you the origin of the Debye's length. So, we will take this equation, and we know what we did before we reached this equation, right. And how we can slightly modify the picture to draw more meaningful insights about the plasma potential is today's objective. So, let us say we start from the distribution of charges. So, in the earlier case we have d square phi by d x square. Now, I have made a shift from r to phi, where x was earlier just a quantity which is just r phi, and r is the radial distance away from the positive charge, right. Now, I am calling x as the position coordinate and phi as the potential itself, right. So, d square phi by dx square can be written as minus E times n I minus n E divided by epsilon naught. You can look into the notes of last class or the class before that, and you will find a similar equation, where earlier we have taken a possibility that the charge multiplied by number of electrons minus number of ions is responsible for giving the charge density. So, d square phi by dx square is resulting from the Poisson equation, and what I have done, what the modification that I have done is that I have not considered a case where number of electrons are larger, invariably larger in comparison to number of ions within the Debye sphere. I have considered a more general case, okay, in which what I am going to do is I will keep minus E by epsilon naught as it is, and since I am allowing the possibility of number of ions as well as number of electrons to be distributed according to their own temperatures. So, by now you must have figured out, generally in kinetic theory we refer to temperature as a single quantity which represents the entire measure of the energy or kinetic energy that is there within the gas system. But in plasma we consider the electron temperature and ion temperature. So, the temperature is different. These two temperatures represent the kinetic energy, the average kinetic energy of electron species as well as ion species. Because of all the things that we have understood about plasma so far, these two temperatures have to be different, right. So, electron, the ion density Ni can be written as n infinity e to the power of minus E phi by kb Ti, right. I will write it here, yeah. So, Ni is n infinity. N infinity is the equilibrium, or let us say we consider the total number of electrons. Ions, Ni e to the power of minus E phi by kb Ti. This is nothing but e to the power of minus E by kt. So, this is, if you have studied any second or first year level BSc, this may have been introduced while discussing lasers, okay. And Ne similarly, Ne is n infinity e to the power of E phi by kBT. You see the disappearance of the negative symbol in the exponential was already discussed in the last class, because within that sphere, the Debye sphere, the number of electrons are extremely large, right. So, that is where it comes actually, right. If you substitute these two things, we can write d square phi by dx square is equals to minus 1 by epsilon naught to E times n infinity e to the power of minus E phi by kb Ti minus n infinity e to the power of E phi by kb Te. Right. Doing some simplification, we can write it as minus n infinity E divided by epsilon naught, taking only the relevant terms. When you expand the exponential in the Taylor series, we can write it as 1 minus E phi by kb Ti minus 1 plus E phi by kb TE, which will be minus n infinity E by epsilon naught times 1 minus E phi by kb TI minus 1 minus E phi by kb TE. So, this will get cancelled, and what we have is this will be approximately equal to n infinity E by epsilon naught minus E phi by kb TI minus E phi by kb TE. So, effectively we can take this minus outside, and all of the right hand side will become positive. Then we can write n infinity E by epsilon naught times E phi by kb TI plus E phi by kb TE, or n infinity E square divided by epsilon naught times 1 by Ti plus 1 by Te times phi. What do we have on the left hand side? We have d square phi by dx square. If we write all of the terms on the left hand side, we will get d square phi by dx square minus n infinity E square divided by epsilon naught times 1 by Ti plus 1 by Te times phi is equals to 0. Let us compare this equation with what we had when we considered the electrons only to be distributed according to their temperature and ions to be constituting a constant background. Okay. What was that equation? This one, d square x by dr square minus x by lambda d square is equal to 0. So, which is d square phi by dr square minus x by, okay, if I am writing everything in terms of x, then I should write x here, x by lambda d square is equal to 0, right. So, now comparing these two equations, what I can write is 1 by lambda d square is n infinity E square divided by epsilon naught into 1 by Ti plus 1 by Te, right. So, lambda d square now has some terms relevant to the temperature of ion as well. Earlier, lambda d is square root of, I think we missed one kb in between, right. So, kb, yeah, kb is here, the Boltzmann's constant. Okay. Did we write it here? Yeah. Now, it should, a kb should appear here, right. Lambda d is equals to earlier epsilon naught kb T divided by n E square. So, in this we thought lambda d is proportional to temperature and lambda d is inversely proportional to the number density, which means at larger temperatures, when you have more energy available to the electrons, they will move more fast and they will not be able to be restricted within a small value of lambda d. Because of the larger velocity, you have to accommodate a provision in which the larger lambda d takes place to nullify the positive test charge. So, the proportionality can easily be explained in terms of physical perception, and it is proportional to 1 by n. That means, more is the number of particles per unit volume, smaller or will be the Debye's length. That means, if there are more number of electrons within a small volume, then obviously the concentration of electrons that you would need to nullify the positive charge are available within a smaller distance. That means lambda d will be small, right. So, both of these things are very well acceptable in terms of easier applying simple common sense, right. How the expression has changed is this, right. So, let us say this is an important result. We will highlight this result just so that it will be easy for you when you look at this lecture notes, right. Now comes the most important conclusion of this discussion. What is it? We can have a situation in which the electron temperature is very large. We can have a situation, let us say 1 is the electron temperature very large in comparison to the ion temperature. We can have another situation in which the exactly opposite may be a possibility. The ion temperature is very large in comparison to electron temperature. So, what will happen in that case? This is the most important conclusion that we are going to draw. So, let us take this expression as it is. 1 by lambda d square is equals to 1 by lambda d square is equals to n infinity e square by epsilon naught kb times 1 by Ti plus 1 by Te. Let us take a situation in which the electron temperature is very large in comparison to ion temperature. So, without actually expanding this term, without actually doing this summation, we can straightforward say that if the electron temperature is very large, this term becomes very small. So, we can neglect it altogether and we can write 1 by lambda d square is equals to n infinity e square divided by epsilon naught kb into 1 by Ti, or lambda d square is epsilon naught kb Ti by n infinity e square. We can write it as the device length is under root epsilon naught kb Ti divided by n infinity e square. We can arrive at the same result saying that, let us say this is the Te Ti and Ti plus Te. When electron temperature is very large, we can write it as Te divided by Te Ti. So, this will get cancelled. You will be left with Ti. That is what we have, right. That means, when electron temperature is larger, the device length is decided by the ion temperature, right. Is it what we are seeing now, right. So, that means the device length, we will write it here, device length will depend on the temperature of colder species, isn't it? This is a remarkable result actually, and exactly when you do it for the case of ion temperature becoming very large in comparison to the electron temperature, the expression will reduce to something like this. 1 by lambda d square is n infinity e square by epsilon naught kb times 1 by Te. I hope you can figure out the algebra by yourself. It is not complicated after all. Yeah, 1 by lambda d square becomes n infinity e square epsilon naught kb into 1 by Ti, which means now the temperature that appears in this expression is not the higher temperature, rather it is the lower temperature, right. So, we can write lambda d is equals to epsilon naught kb Te divided by n infinity e square under root, right. Now, you see these two expressions which are telling a simple fact that under a situation, let us say, if you do not assume that the number of ions or the distribution of ions is independent of the ion temperature, then your expression for the Debye's length is not the same. It will be decided by the colder temperature or the temperature of the species which is colder, right. So, that is why we have these two expressions, lambda d is equals to as a function of Ti when electron temperature is large, and lambda d as a function of Te when the ion temperature is large. So, I will write the conclusion here. So, the conclusion is Debye's length will depend on the temperature of colder species. Okay. Right. So, now we can discuss a numerical based on what we have understood, and then probably this will even help us to visualize the nulling or shielding of the unit positive test charge. Now, having seen this, the effect of temperature on the distribution of ions and electrons and how it modifies the definition of lambda d, we will take up some examples, numerical examples or problems based on the derivations itself to clarify these concepts and to make a more concrete understanding of the Debye's shielding.